Yeah, so we were looking at Hilbert style proof systems, and we in fact saw some proof, and one important theorem that we saw was the deduction theorem, right, which essentially allows you to move subformulae from the right hand side of the provability symbol to the left hand side as an assumption and prove what is essentially. So, in a formula of the form phi arrow psi, phi is called the antecedent and psi is called the consequent. So, it allows you to move the antecedent as an assumption and prove only the consequent. Okay. So, and of course, this deduction theorem, the way that we have proven it is is an if and only if is a characterization. So, it means that you can also move assumptions onto your onto the probability side, and therefore, you have a two-way characterization. The okay, and we did this proof which is fairly complicated, at least for the forward kind of rule. So, what happens is this movement that the deduction theorem allows you to do allows you to greatly simplify proofs, right, because you are allowed to make, essentially you can make more some extra assumptions and you have to prove shorter formulae. That is one thing. So which means that essentially, so what you take as assumption is actually an important part of the proof. So far, the way we have looked at our proofs, we just the assumptions were somewhere in the background, and we sort of understood what we were taking as an assumption, and we actually applied the rules as we are given. So, one possible thing to do is to actually, because of this movement that is possible due to the deduction theorem, one thing is that one will have to make the assumptions explicit at each stage, because essentially this movement implies that at every stage in a proof one might have a different set of assumptions, and they have to be somehow consistent and they should all form a. So, we will use the notion of a sequent. Okay. A sequent is also a metalinguistic formulation, and essentially the sequent essentially will allow us to clearly specify at each stage what are the assumptions and what is on the right side of the probabilities, right. So, what is on the left side of the probability symbol and what is on the right side of the probability symbol. So, a sequent is a meta formula essentially of this kind. So, we will incorporate the turnstile and the assumptions directly into our notion of proof. Okay. So, one of the things that the substitutivity allows you to do is to split up theorems into lemmas and sublemmas, propositions maybe, and also it allows us to incorporate those lemmas that we have proven actually as to be directly incorporated into the theorem. So, formally speaking, if you incorporate a lemma, essentially what you are saying is I take the entire proof tree of that lemma and graft it onto the current proof. A simpler thing would be to just invoke that lemma, convert that lemma into what is known as a derived rule, and use that derived rule instead. So, essentially what we are saying therefore is that we will have in addition to the basic rules, we will have a growing number of derived rules that have been derived. They are like the lemmas that we have already proven, and usually in our proof, instead of taking the entire proof of the entire lemma or reproving that lemma for the current stock of symbols that are being used in this proof, it is a good idea to take that lemma, convert it into a derived proof rule and add this proof rule to the existing body of knowledge essentially of that theory, right. So, those are how we will we will proceed. So, we can have derived rules, and what we can do is, of course, in the case of all these lemmas and theorems that we are going to use, they have their own set of assumptions. So, a sequent form for these derived rules is actually the most suitable thing. So, then you can clearly you can clearly understand whether that lemma is actually applicable in the current scenario in a proof that you are doing or not, and that will become clear from the assumptions. So, we could actually take these lemmas and these meta theorems and somehow somehow express them as derived rules and present them in a sequent form, right. So, that the assumptions are also clear, right. So, of course, the proof that we have already done of reflexivity, for example, is just is something that we can already incorporate. Okay, so this is what we did. So, we can all make it a sequent by just putting a gamma in front, gamma and a turnstile in front, and it becomes a sequent form of the proof, right. I mean, basically, since this theorem was proved without any assumptions, and what that theorem on monotonicity says is that any superset of assumptions also the same proof is valid. So, therefore, you can just prepend all these steps by a gamma, if you like, for any gamma. Gamma could be empty, it could be anything, it does not matter, right. Okay. So, that is what we could do with this with the reflexivity, but what will. So, the other thing, of course, is that since we have already proven reflexivity as a general theorem which holds for all formulae phi, we may also express reflexivity as a derived rule. Yeah. So, and then we can directly invoke this reflexivity, that way our proofs will look shorter, and it will also ensure that our proofs remain non-circular. I mean, we do not assume something that we have already proven, right. Okay. So, now the current state of the art, so to speak, of the Hilbert style proof system is this in sequent form. Okay. So, what I have done is I have put in this extra set of assumptions. So, this gamma could be any set of formulae. Actually, from the point of view of provability, we will usually assume that gamma is a finite set of formulae. Now, gamma could be we will essentially assume gamma to be a set. There are people who become very nitpicky and think of gamma as a sequence. Now, the difference between a set and a sequence is that a set does not allow duplicate elements, but a sequence allows duplicate elements. A sequence allows things to be moved across the turnstile only in a certain order, in a sort of a queue or a stack fashion, whereas sets we will just be more informal about it and take it whenever we want. And if we want to have, in the case of sequences of formulae, many people actually are very nitpicky about also the order in which you also the number of duplicates that you exactly want to keep. Whereas, in the case of sets, we will just assume that we can use a formula as many times as we want without worrying about its usage. But there are interpretations of, there are good reasons to believe in using those strict and rather pedantic methods, which have to deal, which actually come from a purely computer science perspective, which is that you can think of these assumptions essentially as resources that are being used in your proof, and your proof is a program which essentially uses these resources. So, when you think in terms of resources and usage of resources, it does matter whether you have duplicate resources or you do not have duplicate resources. Also, it does matter how the resources are organized, and therefore, in what order you can move things to the left and to the right of the turnstile. Yeah. But we will take a more informal view, we will take a sort of a logical view in which we will just assume gamma to be a set or a sequence as and how convenient to us. If we assume it to be a set, we will also assume that you can utilize the assumptions in gamma as many times as you want in your proof. without any hindrance to that. Right. So, the three axiom schemas k, s and n now look like this with gamma appearing in the turnstile appearing here, right. So, this is, let us say, this is what we call the sequent form. There is a much more rigorous and formal way of specifying the notion of a sequent, but I am not going to go into it. This is going to be my notion of a sequent. Yeah. Okay. The modus ponens rule actually now becomes much, has a formalization which makes it clear that in all the three clauses you should have the same set or same sequence of assumptions gamma. You cannot have different gammas, different sets of formulae floating around for each of these proofs. You have to somehow get them all to the same set of assumptions. Okay. The reflexivity is just this. Since we proved it for all possible formulae, you can make it you can make it a derived rule and a schema with a variable like x. So, essentially x arrow x under any assumption gamma is perfectly fine. The deduction theorem itself can be expressed as two new derived rules, right. So, this actually specifies the movement. If from gamma I have proved some formula of the shape x arrow y, then I can claim to have proved from the assumptions gamma union x the formula of the shape y, right. And similarly, if I have from gamma and x, if I have proved y, then I can claim to have proved from gamma x arrow y, right. So, it is very convenient to incorporate this, otherwise just think of it, the proof of the deduction theorem was quite long and complicated, and if you have to go through that process for every proof that you are going to do, it is going to become very tedious and time consuming and very lengthy. It is simpler therefore to incorporate these things as derived rules, and just use them in their in a substitutable form. So, these are the derived rules so far that we have got, and then the next thing of course is how are our proofs going to look like. Our proofs in sequent form are going to look like exactly I mean very much like that, like they looked before, except that now the assumptions are going to be specified explicitly, right. So, here is the proof tree for the transitivity of arrow. Let us just look at it this way, let us look at it carefully. So, if you remember, we initially assumed, because we were going to use the deduction theorem. Okay. So, we took these three assumptions, phi arrow psi, psi arrow chi and phi itself. From these three assumptions, so gamma 3 consists of these three assumptions, and so from which one of the things I said was that any assumption is provable from that, from itself, right. So, phi arrow psi is essentially provable from gamma 3, and this reflects our set interpretation for gamma rather than a sequence interpretation for gamma and not worrying about the order. The other thing of course is that phi is provable from gamma 3, and by modus ponens essentially psi is provable, yeah, right. So, from these two, and of course, one of our assumptions was psi arrow chi, and since psi is provable, then what we have is this is gamma 3, gamma 2 comma phi is gamma 3. So, from gamma 3 I can essentially prove chi. Okay. Now, I have specified this as gamma 2 comma phi instead of gamma 3, because I am going to use the deduction theorem to move phi to the right. Okay. So, then the assumptions get depleted when phi moves to the right, and from gamma 2 you have essentially proved phi arrow chi, and now the assumptions get depleted more and more as I move each of the assumptions to the right side of the turnstile, right. So, our proofs in sequent form are going to essentially look like this. So, each node of the proof tree is going to be a sequent. So, it is not just going to be a formula, it is going to be a sequent, where when will be informal enough, of course, that when if the assumptions are known or they are not changing, then we will just write it as if each node has each node is a formula rather than a sequent. Yeah. Okay. So, this is the proof, and of course, this theorem holds for all phi and psi and chi. So, which means that we can actually render it immediately as a derived rule of inference, right. So, the derived rule of inference is this. So, one thing is either we can think of it as a derived rule of inference, either as an axiom schema in which we have proved this, which corresponds to the last step of this proof, yeah, or we can actually shorten the proof to this portion and essentially think of it as a proof rule, which gives us the transitivity of logical implication, if you like. Yeah. So, essentially by applying the deduction theorem, we could backwards we could actually move all these assumptions behind, and therefore, you could actually get something like this, right. So, this is so in very often you will find this form of the rule more convenient to use than this axiom schema, because it is a this axiom schema is a huge, I mean this the form of the rule splits it up into smaller formulae, and therefore, it is easier to use than in the form of this axiom schema. But in both cases, both proofs would be equivalent, because in either case you will essentially be moving formulae to the left and right of the turnstile by invoking the deduction theorem, right. So, these two, the axiom schema and the rule of inference, are both essentially equivalent ways of doing things, but we will use, but I think we can use whichever one is more convenient to us at any stage. So, that is why I have given them two different names. Yeah. So, okay. So, that is transitivity of conditional. I have also got lots of exercises for you. You can do this. There is a fallacious proof here which you can look at. There are also some extra rules. This here is an interesting rule. This essentially says if x arrow y arrow z and y holds, then x arrow z holds. Okay. So, this is like, this is something very strange. I mean, it is not you can take out the, you can pull out the in between formula essentially if it holds. Okay. So, and sometimes it is convenient to use this as a rule of inference. So, we will use this in later proofs, assuming of course that you have already proved this. Yeah. Right. Okay. Now, there are some things, our formal theory should somehow be consistent with the known facts about propositional logic and provability. So, one basic thing, one of the things we have so far not used is the negation rule. Remember the n axiom. So, here are two derived rules, which means they have to be proven first. I mean, so right. So, now I am jumping the gun, I am expressing theorems as derived rules, and then you have to come out with a proof. Okay. There is a specific reason why it is in this order, and that is, you will see that is because my proof, at least I am not saying that is a unique proof, but these proofs are quite hard. So, they are likely to be unique. The fewer the number of rules and axioms that you have, the more unique the proofs are likely to be. Okay. Once you add more and more rules and axioms, derived rules and axioms, then you can actually have a combinatorial explosion of a number of different proofs for the same kind of theorem, right. So, in this particular case, actually this so this DNE stands for double negation elimination and DNI stands for double negation introduction. Yeah. So, these are some two basic things that we should prove. So, here is a proof for that. So, for the first time now we are using the negation axiom. So, we axiom schema we had k, s and n. So far we have not used the n. So, for double negation elimination we use this n. So, here so I have not specified the substitutions that have to be performed, but now they are obvious, right. So, which is that okay, I do not have a link for that n rule, but I should have had a link for that n rule. So, anyway, so this rule essentially says not x arrow not y arrow not y no y arrow not x arrow y. I think that is what it right. I mean let's okay, not y arrow not x arrow not y arrow x arrow y. Okay. So, essentially I am substituting phi for y and not phi for x, I think. Yeah. Okay. So, let's go back to that. Phi for y. So, I get not phi here and not phi for x. So, I get not phi here, and this is y and this is not x arrow x y, phi for y. Okay, yeah, y. Okay. So, this is an instance of the rule n, and of course, we have already proved for all formulae we have proved the rule r arrow. So, this between thing not phi arrow not phi holds, and therefore, I can conclude and from R2 which was the previous one where you could remove this middle thing if you have proven it. It follows that I can remove this middle portion not phi arrow not phi to give me not phi arrow not phi arrow phi. Yeah. Okay. Then from k of course, you get not phi arrow not phi arrow not phi, and we have the transitivity of the conditional applied to these two, right. So, not phi arrow not phi arrow not phi and not phi arrow not phi arrow phi. So, these two give me not phi arrow phi, and then I move this antecedent to an assumption and I get not phi proves phi, right. I mean it is not at all easy to think about these proofs, but it becomes much easier once you have a collection of basic theorems, and basic therefore, in our case basic derived rules, yeah, some fundamental derived rules. Okay, this the double negation introduction requires using triple negation, because you have to. Okay, so here is the first application of the n rule with y being not phi, x being phi. Yeah. So, you do that substitution and you get this, and this double negation elimination can already be taken as a rule in which I can take triple negation phi arrows single negation phi, right, and then I can apply modus ponens, I can get this. Again I can take an application of the k rule, and then I can apply transitivity of arrow to give me phi arrow not phi, and then I can move phi to the left of the turnstile. So, you can see that I have mixed I did not start actually in a sequent style, but that is because you assume that if I do not put it in a sequent style, then I am assuming an empty set of assumptions, gamma is empty, right. So, when I actually move the when I get into a sequence style, I put in the turnstile whenever necessary, right. So, this is all informal. Most logic books would actually go either completely rigorously in non-sequence style or completely rigorously in a sequence style, but we will mix these things, because then it becomes too pedantic otherwise. So, it is a good idea for us to mix it, provided we make sure we know what we are doing and that we are not inconsistent in any way. Yeah.
Not have a situation where we use these derived rules to prove k and s too, so that we would really need to use these odd looking rules k and s.
Once you have got a sufficient number of intuitive derived rules, it will not be necessary to use k and s, okay, because you will most of the time be using them, using the derived rules. But you have to look at the philosophy of Hilbert style proof systems, right. You are looking for a minimal set of axioms and rules of inference from which everything else can be derived. So, therefore, for your initial basic theorems, you will require k and s, k, s and n actually, as we have seen. In fact, without n we cannot have proved this. See, what I am trying to say now is, look at this. Once you have got these two rules, it becomes very convenient to reduce an odd number of negations by removing by removing an even number of them and simplifying them, right. But the point is, to get these derived rules, you do need to use the basic rules, right. And David Hilbert in his greatness came up with these two rules, k and s and n, right. And actually those rules are complete. I mean, you require only one proof rule, that is modus ponens, and in fact all logics would have a modus ponens rule, and he just requires 3 axiom schemas. But till you have derived all those all your important basic theorems, you will not you will have to use the you will have to use k and s.
So we can derive it. We can have a set of rules, derived rules, which can.
Yeah, that is what we are going to do. That is what we are going to do. We are going to do it for our convenience. Yeah, you can have a set of derived rules, yes, which you can completely use, as we will see. Right. Okay. So, there is another version of the Hilbert style proof system, which instead of n uses n prime. Okay. This looks somewhat simpler and actually more intuitive. You know, it is well, the converse of it is that if x implies y, then not y implies not x, right. The converse of it would be that, but this is somewhat simpler too. So, it is possible to remove n, put in n prime instead, keep the k, s and the modus ponens rule as they are, and still get a complete system. And these exercises here I will ask you to prove that. For example, can you derive n from n prime? That is one question, right. Can you do the deduction theorem in this new system h naught prime? Well, the deduction theorem did not use n or n prime. So, the deduction theorem will actually hold without any change, right. So, you will get those derived rules anyway. The only thing therefore, you need to do is to prove n from n prime, and then after that you can essentially follow Hilbert's, right. So, so these things actually tell you, these exercises are meant to show that there may not be a unique system, there may not be a unique minimal system. You can have more than one unique more than one minimal system, and this is a slight variation of that. The next thing of course is okay, this n double prime is the actual contrapositive that I was talking about. If x arrow y, then not y arrow not x, right. But of course, we are talking about syntax, right, in our proof theory, pure formal proof theory. So, you cannot assume that n prime and n double prime are the same, they both have to be derived by using only k, s, n and whatever derived rules you have proved so far. Okay. So, as a general principle, we will assume that whatever we have proved so far we can use, right. That is how theories are built. Okay. But this is how, for example, Euclidean geometry also works. There are some basic axioms and postulates about lines, planes and points. Using just those basic axioms and postulates, you prove some elementary things, and later actually in the later parts of Euclidean geometry, you hardly refer to these postulates. You always use the previously proven theorems, right. So, that is exactly what will happen in this case too, right. Okay. Okay. So, there are there are certain things, for example, there is a, we should not lose sight of the fact that we have certain basic principles in mathematics, right. One is proof by case analysis. That is something, especially in computer science, we keep doing a lot of that. Structural induction is really like case analysis or so on. So, proof by cases is a rule that you have to justify. So, this rule, it says gamma, if gamma x proves y and gamma naught x also proves y, then gamma proves y. Okay. There are two ways to interpret this, either that the truth of y depends only on gamma and does not depend on x or not x, but very often we do case analysis. Supposing this were so, so there are two possible cases, either this is true or this is false, and then in both cases it leads to y. So, you can think of this as a proof by cases, justifying the proof by cases, and that the Hilbert system allows you to derive this proof by cases rule, and therefore allows you to use proof by cases. And most importantly, indirect proofs methods, there is proof by contradiction. So, from the assumptions gamma comma x, you can prove both not y and y, then from gamma you can claim to have proved not x. This is our standard proof by contradiction, right. So, and this can be proven also as a rule. I mean, so these are things that you have to do. So, these are certain basic proof methods which we have to justify, right. From the main question is, does the Hilbert system with just those three axiom schemas and one rule of inference, is it powerful enough to capture these kinds of proof methods that are used in mathematics? And the answer is, if you can derive these rules, that it can actually give you these proof methods. Yeah, right. Now, the next thing of course is that the Hilbert system was minimalist in more ways than one. Firstly, it used only two operators. Okay. So, whereas most of the time when we think of propositions, we think in terms of and, or and not, that is our normal, things are intuitively clearer when we think of them in that form. But Hilbert chose this adequate set consisting of just not and arrow. From a minimalist viewpoint, what it also what it means is that it simplifies the number of cases he has to consider in all his proofs. Okay. If he has to prove any properties about his system, he needs to consider only two operators, and if they are adequate, then that is it, that is enough. But if we are going to come up with derived rules, we might as well also come up with derived operators. Okay. So, our common and intuitive operators can be defined as derived operators. Yeah. So, this is the standard definition for these operators. Okay. So, and for completeness I have given all of them, right. Since we had this language P naught, right, essentially we are interested in the language P naught, whereas Hilbert forced us to look at a very small subset of the language P naught with P naught with L naught. Yeah. Okay. Of course, the other thing is you can define any other new operators you like, NAND, NOR, XOR, maybe a ternary operator, maybe if then else, maybe a quaternary operator, maybe a fivery operator, sixery operator, whatever. But since you have not and arrow as functionally complete sets, as a functionally complete set of operators, just express this whatever new operator in terms of not an arrow. Okay. Now, it is fine to have these derived operators, but it is useless unless you can use them also in proofs. Okay. So, just like we did in the case of double negation, the natural thing to do is to actually come up with operator elimination and operator introduction rules. Okay. So, remember that this is definition, this is a definitional equality. Okay. There are other kinds of equalities we have looked at. Syntactic equality was one thing. The other equality, then we looked at logical equivalence, for example, that is an equivalence relation, but that is a congruence. But this is an equality by definition, and since it is an equality by definition, what you are saying is that what is on the left hand side is just an abbreviated name for what is on the right hand side. Right? I mean, this is what a syntactic definitional equality essentially says this, that I am using this symbol on the left hand side as an abbreviation of a certain structure, a certain pattern on the right hand side. Okay. So, what we need, our proof system of course, otherwise will. So, whenever, that means by definitional equality what we are saying therefore is, any time in any proof we encounter one of these left hand side symbols, we should be able to replace it by its definition on the right hand side. Similarly, if any proof you encounter a sub pattern which conforms to this kind of to one of these patterns, then I can replace that entire sub pattern by a left hand side form, right, and that is exactly elimination and introduction. If you encounter this operator, then I can eliminate it by using the right hand side body, is definitional body, and if I encounter this pattern any time in the proof, I can replace it by the left hand side and abbreviate it basically, right. So, the natural thing to do, just like in the case of derived just like we did in the case of double negation, the most natural thing to do for any new operators that you might define is to have an elimination rule and an introduction rule. So, now you can prove theorems also about these derived operators, right. So, or and so on and so forth. So, this of course, so what we are saying is there is some you have a definition of each of these operators expressed entirely in terms of tree structures. By the way, these are supposed to be trees, right, I mean tree skeletons with hooks. The purple x1 to xn's are the hooks on which you can hang other trees, right. So, these are so you can think of these hooks also as being classified into n different types, n different colors only. So, to distinguish them. So, I might have more and more I might have more than one occurrence of x1, but what I am saying is x1 is not the same as x2, but nothing prevents me from hanging copies of the same object in both x1 and x2, even though x1 and x2 are not necessarily the same. I mean, so everything that you learnt about substitution of variables actually comes up here. So, these are skeletal structures, or these operators are defined as essentially skeletal structures with placeholders with names on them, which identify two places with the same name and distinguish two places with different names, but do not prohibit the two different placeholders from having the same object or copy of the same object on them. Yeah. So, if I have an operator O defined in terms of some skeleton omega of my basic and derived operators, just like I can use my derived rules, now I can also use my derived operator. Why not, right? And I can every time in any proof, if I encounter this operator O, I can replace it by its definition. And any time in any proof, if I encounter a pattern which corresponds to this pattern omega, then I can replace it by its left hand side, right, by preserving the names of places and the colors of places as they are. That is important. Yeah. Okay. So basically for all derived operators you just require some elimination and introduction rules. Yeah. And then whatever you get is as complete as Hilbert's original system was, except that things become somewhat more intuitive, somewhat more convenient for you to use, that is it. And in fact, what happened was that was one of the things that I spoke about previously, right, that there are two conflicting desirable properties of a proof system. One is minimality, which is essentially inspired by Euclid's and the controversy over his parallel postulate, and the second thing is naturalness, right. How natural is it to apply certain rules? It is clear that this, I mean, some of the proofs that you have seen are murderous, right. I mean, it will never do to be able to think about it like you require basically unlimited amount of time if you have to ever come up with that proof, and then there is no guarantee that you will be able to come up with the proof, right. But so naturalness is something that gives you certain handles, syntactic handles on how to probably go about your proof system. And one of the prime and the most famous natural proof systems is that of Gentzen. Yeah. So, Gentzen's natural deduction system is something that is very similar. I mean, the Gentzen's natural deduction system is what inspired this way of most of you in your programming languages course would have learned about structural operational semantics. Yeah. So, the structural operational semantics is given in terms of proof rules. So, it is actually a proof theoretic way of looking at the computations through these rules, through the operational rules. What also, so what is structural about it? What is structural about it is the fact that for each operator in the language, in the programming language, there are one or two rules. There is a complete set of rules which allow you to deal with the computations of that operator, right. So, it is structural in that. So, all properties of the system of SOS rules are essentially proved by induction on the structure. Okay. Each transition in the SOS system actually gives you a sort of a proof tree, which is based on structure and breaking down the structure into smaller structure. And actually we have seen this in the form of tableaus earlier, even here, right. Breaking down a given syntactic structure into its components. Using that breaking down policy, that is somewhat more natural. So, in fact, the tableau system itself was inspired by Gentzen. Okay, Gentzen. So, both Plotkin's structural operational semantics for programming languages and Smolyan's tableau systems were actually inspired by Gentzen's natural deduction. So, he actually called it natural deduction because he said it is the most natural way to try to do deduction with syntactic objects. You look at the syntactic object, it has a sort of a tree structure and it has a root operator. You apply some rule for the root operator and express it in terms of the subcomponents of that tree of that syntactic object. Okay. So what it means is that, and then of course, you should be able to form these you should be able to not just break down syntactic objects, you should also be able to form these syntactic objects from proofs, right. So, he had both introduction and elimination. So, in fact, whatever I have written about introduction and elimination is related to essentially Gensen's system. Yeah. So, we will present a Sequent version of the system. It is not exactly what other people present, but I think it is a good adequate system. Further, there is some redundancy in the rules. Very often we are in logic, we are interested in preserving certain symmetries rather than check for minimality. Once you have decided that minimality is not important, other aesthetic considerations are as important or more important, then there is some redundancy in rules. In fact, some of the rules will never be applied at all, but they are there for a kind of maintaining a symmetry of the chart. Of course, one thing is that when you have these redundant rules, you have to ensure that your system does not become unsound, does not become inconsistent. That is a matter of concern. So, we will call this system G naught after Gensen, right. So, now you take all the operators that we have in P naught and define introduction and elimination rules. So, for example, take this top introduction. Basically, what we are saying is that top can be introduced anywhere. I mean, top is true. Yeah. So, but the point is you are never actually going to use this rule anywhere. I mean, it is not going to be of much use. Okay. But just in case, for completeness, to preserve both sides, we do this, right. Bottom introduction, well, anytime I have a contradiction in my proof, I can claim bottom, right, which is exactly the form of bottom, right. I mean, the definition by sort of definition. And if I have ever proved a contradiction essentially, then I can actually infer anything I want. You take a set of assumptions or axioms. So, a system is inconsistent if all the formulas in the system are provable. Let us go back to inconsistency from a model theoretic point of view, from the semantics, right. A set gamma is inconsistent means that it has already got a contradiction. So, and of gamma would imply any formula, would imply each and every formula in the system. Okay. A corresponding analog for provability is that if a system is, if your set of assumptions is inconsistent, then you can essentially conclude anything you like. Any formula of the system is then a theorem of that system, is a provable consequence of that set of assumptions, right. Okay. So, these are the introduction and elimination rules for bottom and top. These are for negation and double negation. We have already seen that. I mean, so gamma x bottom, then gamma proves not x. Gamma not x proves bottom, then gamma proves x. And so you can see that they are not completely mutually exclusive everything. We are just filling up all the gaps in the pattern by. Okay. So, this is the negation, double negation introduction and double negation elimination. We do need one of these at least, but and then you have OR introduction and OR elimination. Yeah. The interesting thing, of course, so OR introduction is very simple. You can introduce, if you have proved x from gamma, then you can introduce any y, it does not matter, and but the elimination is interesting. So, essentially what you are saying is, if you have proved two cases x or y, if you have reduced your notion of proof to just the truth of x or y, and if x from x you can prove z and from y also you can prove z, then you do not require the case analysis x or y. So, this is a more generalized form of case analysis, and it says from gamma you can prove Z, right. Okay. And introduction is very simple, you have to be able to prove both of them in order to take a conjunction, and elimination is very simple, you have to prove the conjunct and then you can take any component of the conjunction. Arrow introduction is very much like our deduction theorem. Yeah. So, if from gamma and x you can prove y, then you can claim that, hey, I am sorry, this is wrong, it should read gamma proves x arrow y. Yeah. Okay, I will correct that. This is the modus ponens rule, arrow elimination is just the modus ponens rule. And then but the biconditional introduction and elimination are just as in, I mean they just it is just the biconditional is just viewed as a conjunction of the arrow and its converse. Yeah, that is right. So, these are all the things. The other interesting thing of course is, so these are, so you can see that, so Gensen's system has a natural structure in terms of operators. So, for each operator you have introduction and elimination rules and you can use them in a definite instead of making it in a definitional form like we did before in the Hilbert style proof system, you can explicitly use these rules. Yeah. Okay. So, now your job is to prove all of Gensen's rules from the Hilbert style proof system. That is an exercise. The other thing of course is all those logical equivalences should be provable as two-way conditionals in the Hilbert style proof system, or some of them are already there in the natural deduction proof system, but the others may have to be proven, right. So, with this but what we still have to worry about are a few things, soundness and completeness. The soundness of the systems are quite obvious, because all our axiom schemas are essentially structures of tautologies, at least in the Hilbert style proof system, right. And you just have to prove the soundness of modus ponens, okay, that if and the only important question is it complete? That means, can all logical consequences be also proven? Now, what happens is, are there things called infinitary proofs, infinite proofs? Are there some logical consequences which are only consequences of an infinite set of axioms, infinite set of assumptions? Well, the compactness theorem tells us that that is not true, that is not possible, right. So, it is possible with just a finite set of assumptions to prove a logical consequence. So, which means you should be able to get finite proofs for all. So, our completeness is enough to restrict it to the question when gamma is a finite set, and we have to show that it is complete. So, we will do that. I will stop here.